energy. And that was Eddington's great realization, that you can take lots of these little protons and combine them together to make helium, and you will get some energy left over. Eddington only made this realization once the masses of the nuclei were measured very accurately indeed. So what happens is that the nuclear energy is produced in the center of a star like the Sun, and we've got on the graphic here a demonstration of how it is that the Sun then is held up. Energy is generated in the center by nuclear processes, and that energy generation produces a pressure which counteracts the attractive force of gravity. Now remember, in astronomy, gravity is always trying to pull things together to make things collapse to a point, and it is resisted by pressures of various sorts. In this case, it's the pressure of the hot gas which has been heated up by the nuclear reactions in the center of the Sun. Let's open up this big model of the Sun to see what the inside of the Sun really looks like. Thank you, Bryson. Here is our big Sun. Now, this is a very beautiful model, and how the Sun works is that the nuclear energy generation takes place in the central 10% by radius of the Sun, just this central part here. And we should look at the nuclear reactions which take place, because we're going to need that later. On the next picture here, you will see how to convert 4 of the positive protons into a helium nucleus. It goes through a number of stages. I look at this bottom channel, since they're both the same. 2 protons combine together to produce a deuterium nucleus, which is the heavy isotope of hydrogen, a proton and a neutron, and throws out a positive electron, a positron in that process. Then another proton enters the scene to create a helium-3 nucleus, and then 2 helium-3 nuclei combine together to make helium-4, throwing off 2 protons at the end of that cycle. When you do the sums, you end up with a generation of energy when you convert these 4 protons into 1 helium nucleus at the end of the chain. And that is the process which keeps the Sun shining. What then happens is a great deal of energy is generated in the nucleus, and then that heat diffuses out through the Sun. In the center, the temperature is about 10 million degrees, so that the nuclear reactions can be sustained, and then it cools on the way out. There's radiation out to this, roughly this region here, and then in the outer layers of the Sun, there's a large amount of convection. The outer layers become unstable, and energy is transferred outwards by convection. It's similar to the process when you're boiling a kettle and you see these big eddies set up. In the outer layers of the Sun, there's this convection which carries the energy out to the surface. The temperature here is only about 6,000 degrees, and as we learned in the last lecture, that means it radiates in the optical waveband, and that's why the Sun shines. Now, how do we know that's correct? Because after all we can see from the Earth is the surface of the Sun, and we have had until recently to infer rather indirectly what happens inside. Now, there are now 2 magnificent ways of looking inside the Sun, deep inside the Sun. The first of these is to look for particles which can escape directly from the very center of the Sun right out through the dense outer layers. Now, these particles are called neutrinos. They're very weakly interacting particles, which means that they hardly bump into anything at all. For example, from the Sun, there are 1 million billion neutrinos every second passing through 1 square meter of this lecture theater. Have you felt any of them? No, because they pass right through. They've got essentially no interaction with matter at all. And that is why they can escape from deep down inside the Sun to the Earth. Now, this provides an excellent test of our theory of the interior of the sun, because we should be able to detect these neutrinos. Here is one chain by which they are produced, which has produced a very important result. You remember there was some helium-4 and some helium-3 produced in our cycle. These can combine together to make beryllium-7. When a proton is added on, that makes boron-8, which then decays to beryllium-8, and in the process releases these very weakly interacting particles, the neutrinos. Then the beryllium-8 decays instantly into 2 helium-4 nuclei again. So the game is easy. Sorry, it's difficult. What you've got to do is to try to detect these very, very weakly interacting particles on Earth. Now, what one does then is to take some species which has got lots of chlorine nuclei in it, and very, very rarely, one of these chlorine nuclei will be hit by a neutrino and be converted into an argon nucleus. Now, that's wonderful, because that argon nucleus is radioactive, and therefore what you can do is to measure the amount of radioactivity which is produced in the substance, and that will tell you how many neutrinos have been detected. Because they're so difficult to detect, you need enormous apparatus to detect them. And on the next slide, I show you here a picture of the famous Davis neutrino experiment, which is carried out in the bottom of a gold mine in South Dakota. It's got to be put very far underground so there's no background signal coming into the tank. In this huge tank, there are about 100,000 gallons of cleaning fluid, a stuff called perchlorethylene, which is absolutely crammed full of chlorine nuclei. So that experiment has been running for 20 years, and there is good news and there is bad news. The good news is that the solar neutrinos have been detected, and that's wonderful, because we would really worry if we had not found these neutrinos. The bad news is that there's only 1/3 as many as there ought to be. And that's very worrying, because it means we're not quite sure whether our model of the nearest star that we can study, our own sun, is correct or not. Have we got the nuclear physics wrong, or have we got our structure of the sun wrong? Now, fortunately, we've now got another way of studying the inside of the sun. This is by what is called solar seismology. Now, we're going to have a little apparent diversion for a musical interlude, and I would invite the people here in the second row. Would you like to stand up, please, and raise the objects that you were provided beforehand? Now, you will see that my friends here have each got bells. Now, let's see what happens. We'll just send them off in sequence. Ready? Good, thank you, excellent. I think that deserves a point. Having had the rehearsal, we'll now have the performance. We'll do it again, right? Ready? Thank you very much. Excellent, excellent performance. I'll take the big one. I'll take the big one. Thank you very much. Now, you would be right to ask, what on earth has that got to do with the sun? And the answer is really very intriguing indeed. You see, if I was very clever, I could work out from the tone that we've just heard what the internal structure of this bell was. For example, you heard that the high note, like this, came from the little bell, and the deep tone came from the big bell. Now, what we can do is to do the same thing for the sun. If we kick the sun, it will also resonate like these bells at its natural frequencies. And the wonderful thing is that these resonant modes of the sun have now been detected. It's one of the most exciting aspects of modern solar astronomy. And here on the screen are 3 examples of the way in which the sun can resonate. It just resonates like a bell, only the velocities involved are very, very tiny. This picture here, the yellow areas are showing positive velocities of a few centimeters per second, and the green ones are going away from you at a few centimeters per second. And the magnificent thing which has happened is that one can now detect these modes of oscillation of the sun. Now, why is that so important? The reason is that some of these modes correspond to waves going deep down into the center of the sun. And therefore, if you select the correct mode, you're able to work out the properties of the interior of the sun by these oscillation experiments. Now, how do we kick the sun? Well, it's very simple. There's all this turbulence and convection in the outer layers of the sun, and that's quite sufficient to cause disturbances in the center of the sun. So let's have a look at some of the earlier results in this field. It's really a very beautiful experiment. Here is a graph showing the square of the speed of sound inside the sun. Now, that is related to the temperature and density and pressure of the gas inside the sun. And along this axis, we've got the radius within the sun. Here is the outer radius of the sun. Here is its center. The dashed line shows the theoretical expectation, and the solid line shows the observations. You will see that in the outer 75% of the sun, the agreement is extremely good, and that's very encouraging indeed. In the middle, there seems to be a bit of divergence, but these particular experiments were not too sensitive to the interior regions of the sun. Now, one of the most exciting results, which was only published at the beginning of this month, is that the Birmingham group have now carried out experiments which probe right into the very center of the sun. And their exciting result is that it looks as if the astrophysics is correct. That makes me very happy, being an astrophysicist. What it means is that we can use our models of the sun and use it to find out what modifications are needed to the nuclear physics which we've put into the models of the sun. And that's very important, because what we're hoping then to find is new information about nuclear processes by a purely astronomical experiment. Now, we ought to talk about how then stars evolve. We now understand how the sun works, and the theory really is very refined nowadays. Let's look at how stars evolve. Now, I've got on the screen here a beautiful time-lapse picture of how the stars evolve. This is the whole of stellar evolution in one picture. It's a form of time-lapse picture, and you remember these beautiful pictures of how flowers develop. You have a little seed in the pot, and then you click the shutter every hour, and then when you run the cinema film at the proper speed, it goes whoosh, right? Well, this is exactly the same experiment, but in this case, we are opening the shutter of our camera every 3 million years. So the total time sequence around this track here is a very, very long time indeed. Now, this shows how the stars then evolve. We're going to show in the lecture that they're born in large clouds of dust and gas, and they settle down very rapidly to burning hydrogen to helium in their cores. And that is a very stable process. Most of the life of a star is spent in this process of simply burning hydrogen to helium for a long, long time, all the way around this track here. And the death throes of the star take place in a very short period compared with the main lifetime of the star. Our own sun is round about halfway through its track. We expect the total life of the sun will be about 10 billion years, and the sun is at the moment only 4.6 billion years old, so we've got no problem with the sun running out in our own lifetimes. It's going to be there a long, long time after we have gone. Most of the stars which are close to the sun are, in fact, in this state of burning hydrogen into helium. Now, what happens towards the end of the lifetime of the star? What happens is that when about 12% of the hydrogen of the star has been converted into helium, then the core of the star starts to collapse. It has to get hotter to find a further energy source. And when that happens, the outer layers of the star start to expand by an enormous factor. In fact, they expand by such a huge factor that we end up with what we call giant stars, which have got diameters thousands of times the size of the original star. When they expand to this large size, they also become cooler, which is why they've got this red color. That's what happens to the outer envelope. What happens to the inner regions? Well, the inner regions keep contracting, and they start burning hydrogen from helium into carbon. 3 of the helium nuclei can come together to make carbon, and possibly we even go further to burn carbon and oxygen, and in this way begin the production of the heavy elements, carbon, oxygen, possibly even through to iron. But eventually, even that nuclear process ends, and the star collapses to some form of dead star, either a white dwarf, a neutron star, or a black hole. And these stars we're going to talk about in detail in the next lecture. Now, when that final collapse takes place, the whole of the outer layers of the star are blown off. And you see, this is a beautiful process, because what happens is that the stars cook the elements and produce things like carbon, oxygen, maybe even up to iron, and then an explosion occurs which recycles these cooked elements back into the interstellar gas, ready for the next generation of stars. And this is what I call the great cosmic cycle. We make the stars from interstellar gas, they evolve and burn hydrogen into helium for a long, long time, and then they explode and return cooked material to the interstellar gas. This is the great cosmic cycle. Notice that our bodies are made of things like carbon, oxygen, iron, and all of these were made inside stars and dispersed through the interstellar medium. So bits of all of us have been through a supernova explosion. Think of that. We've all been there at some stage. Now, for the rest of this lecture today, I'm wanting to concentrate upon how to make stars. This is one of the great problems of modern astronomy, because we need to understand how to make stars if we're to understand how to make galaxies with stars formed in them. You can see one of the problems in this slide is that the stars form rather rapidly. And so we've got to catch them just at the right moment in order to see the process of star formation occurring. Now, let's then look at the region of star formation which is closest to the Earth. We know there are some very massive young stars present in this region, and it's in the constellation of Orion. On the next slide here, I've got a lovely old picture of Orion the Hunter, where there are the 3 stars along his belt, and there are other stars down his sword, stars at his shoulders, and stars at his knees and feet. And here is a beautiful, large-scale picture of the constellation of Orion, which I'm sure you will have seen in the sky, with the 3 stars of the belt, and then the sword coming down here. Here are his shoulders, and here are his knees or feet, however you wish to interpret the picture. Now, the region which we're going to say a great deal about in this lecture is the Orion Nebula, which is this region here in Orion's sword. Now, on a clear night, I very strongly recommend you to take a pair of binoculars and go out and look at Orion's sword, and you will get a quite magnificent view of the Orion Nebula. It'll be a bit fuzzy, because the air in this country is rather unstable, but do have a go at trying to see the Orion Nebula for yourself. I've got on the screen here a very beautiful image of the Orion Nebula, taken by the Anglo-Australian Telescope, and the nebula itself is being excited by 4 very young bright blue stars in this part of the nebula here. They're emitting lots of optical and ultraviolet radiation, which is exciting this beautiful filamentary structure that we see on the picture. These bright blue stars are about 1 million years old, and so they're quite young, but they've already done it. They've known how to make themselves. What we want to do is to find the stars which are much younger or even in the process of formation. Now, there's one very obvious problem with this picture, and that is that you can see there's a great deal of dust scattered all over the picture. And in fact, the dust is obscuring many of the most important regions that we wish to study inside the Orion Nebula. Let's look at the next picture, which shows the Horsehead Nebula, one of the most beautiful pictures in astronomy. And although the Horsehead looks very beautiful, in fact, it's just dust, which is obscuring what there is behind it. And in fact, there's a huge dust cloud here, which is why we see so few stars in this region. And the Horsehead Nebula is simply one bit of dust, a dust cloud, which is bubbled out of this large region of dust. So how can we see through these very opaque regions to what is going on inside? Now, the thing to appreciate is that the little dust grains which are doing all of the absorption of the radiation are around about 1/1,000,000th of a meter in size, 1 micron in size. And the reason that the dust grains are absorbing is that the wavelength of the light is smaller than the size of the grain. If we can look at rather longer wavelengths, which are bigger than the size of the grains, then the dust becomes transparent. Now, we want to demonstrate that to you in the lecture theatre here. Two of my colleagues from the Royal Signals and Radar Establishment, Peter Dennis and Mike Perkins, have very kindly brought down a magnificent infrared camera with which we are going to observe a model of the constellation of Orion. Now, here is this wonderful camera. It works at a wavelength of 10 microns and is an entirely new technological development. The magnificent thing is that it can work at this long wavelength without needing any cooling. This is the first of its type in the world. What we're going to do is to view this model of the constellation of Orion through this box into which Bryson will eventually pump smoke with dust particles which are roughly the same size as interstellar dust. Now, at the same time, we're going to view with the television camera through the same box so that we can get simultaneously the infrared and the optical picture of the constellation of Orion. Now, you will see here the images obtained by the two cameras. The one on the left is taken with the infrared camera working at a wavelength of 10 microns, and here is the television camera working in the optical waveband. Right, Bryson, let us now put the interstellar dust in between the observers and the constellation of Orion. Now watch what's happening. As Bryson keeps puffing more and more smoke into the box, you'll begin to see that the optical stars are beginning to disappear, while in the infrared, look, the constellation is still there. Here, we've almost got the stars of the Orion constellation disappearing. And we'll better stop the experiment before Bryson dies. Thank you very much, Bryson. This really is a magnificent demonstration of how it is, by going to the long wavelengths, we're able to see through dust into what is going on inside these dusty regions. Now let's look in a little bit more detail at exactly what's going on, because we're now going to apply these ideas to astronomy. What I've got here is the spectrum of a star, which we're going to suppose is behind a dust cloud. You will see here the wavelength, just shown schematically, the ultraviolet, the optical, and the infrared waveband. Now, what is happening is that when we pass this spectrum through the dust cloud, then the optical and the ultraviolet radiation, which have got shorter wavelength than the dust grains, they are absorbed strongly by the dust. However, when we look at 10 microns here, you see that is larger than the size of the dust grains, and so we don't get the attenuation or absorption of the radiation. But what happens to the radiation which is absorbed by the dust grains? Well, what that does is to heat up the dust grains to a certain temperature. and then the dust grains will radiate at the temperature to which they are heated, just like little black bodies. When you work out what the temperature of the grains will be, it turns out to be about, say, 30 to 100 degrees Kelvin, rather cold, but that immediately tells us from our temperature wavelength relationship that the radiation will come out in the far infrared waveband. And here we've shown schematically here the radiation now coming out, the re-radiation by dust of the radiation which was absorbed in the optical waveband. What's happening, you see, is dust is acting like a transformer. It's taking the optical radiation and converting it into long wavelength radiation, which can then escape from the dust cloud because it's got wavelength much greater than the size of the dust grains. So let's look at our own galaxy again in these different ways. Here's the picture which we've looked at before of the plane of the galaxy here. This is the center of the galaxy in this direction, the north pole of the galaxy here, looking vertically up out of the plane here, and looking down below the plane of the galaxy in this direction. It's a beautiful picture, but you can see it doesn't really look very much like a galaxy, because look at all this obscuration by dust here. It's making the distribution of the starlight very patchy. So when we now look at the galaxy in the infrared waveband, we get a much clearer view. This next beautiful picture, a fantastic picture, was only obtained within the last year by the Cosmic Background Explorer satellite. This is a picture of the galaxy at 2 microns, and it's absolutely convincing that we live in a spiral galaxy with a disk and a bulge in the center. It looks rather like the next galaxy, which again is a picture showing a central bulge and a beautiful disk. Now, what happens then to the radiation absorbed by the dust? It gets re-radiated at the long infrared wavelengths, and then when we look at that wavelength band using the infrared astronomical satellite, we see this picture. This is a picture of our galaxy at about 60 to 100 microns, exactly corresponding to the temperature to which the dust grains have been heated up. And so this is now dust not absorbing, but dust emitting radiation, having been heated by the stars. Now, until recently, it has been very difficult to make maps of these regions of star formation in the infrared wavebands. But within the last 4 or 5 years, we've now had the infrared equivalent of television cameras, very, very sensitive devices, to look at the sky. And I thought I'd like to show you how we make observations nowadays. This not only applies to infrared astronomy, but to optical and many other sorts of astronomy as well. Now, before you can do infrared astronomy, you've got to go to a superb site for being able to observe the sky. And the best site for infrared astronomy in the world is on the summit of Mauna Kea, which is an extinct volcano in Hawaii, which may explain to some of you my shirt. In fact, when I tell my friends I'm going off to Hawaii to do astronomy, they say how lucky you are to be going to Hawaii. What they do not realize is I'm going to the top of a mountain at 14,000 feet, where there's only 60% as much oxygen at sea level, and it's not all that pleasant. However, the astronomy is more important, and it is a magnificent sight. The air is very clear and very dry. Here is the UK Infrared Telescope, which is run by the Royal Observatory in Edinburgh. And the next slide shows you this telescope. It's the world's largest dedicated infrared telescope. And on the back, we've got this magnificent infrared camera built by my colleague Ian McLean, who is shown on the next slide, filling up this camera with liquid nitrogen, because we've got to keep the infrared detectors very cool. The next slide shows that we no longer sit on telescopes to make observations. We can sit inside warm control rooms and do everything remotely. Now, I thought you'd quite like to see what we do to make observations nowadays. We point the telescope at the correct bit of sky, and then we integrate for a certain time. But these are electro-optical detectors, and we don't get a very clean picture when we start off. I'll now just press the return button on this monitor, and we will see the type of data which we get coming directly out of the telescope. And you will find it's not very impressive. The reason for this is that we have optimized these chips to give them maximum sensitivity, and so they're very sensitive to imperfections in the detector chip itself and also to variations in the sky brightness. And so although you can see a star here and something here and something here, it's really a great mess. So what we do is to now look at the sky, a blank piece of sky, in order to find how the sensitivity of our detector changes as a function of position on the chip. Often we just simply look at a blank piece of sky in order to see what the sensitivity response of the detector chip is. And here's what you see. You see there are some dead pixels, some dead picture elements on this slide, and also variations in sensitivity. When we convert this into a color image, you'll see there are these stripes across the chip which we have to take out. But we can then divide that out to get a very deep and sensitive picture of the area of sky that we're interested in. And after a bit of processing, this is what turns up. It's a beautiful picture. Once we correct the sensitivity of the detectors, we can see these stars very clearly, but now in addition, lots of structure. You can see this beautiful structure, arc-like structure up here in color. There may even be a sort of jet coming here. This is in the infrared, and so it's free of dust. If we look at the same region in the optical waveband, which is shown in the next slide, you'll see that we can see the same sort of structures, but this really we can't distinguish at all because there's lots of dust which is messing up the image. The infrared image shows us, if we just flick back to that one again, all the structure there is here. It's as if there's a bow shock being forced through this bit of the gas cloud by a jet. It's a beautiful example of how we do astronomy nowadays in the infrared waveband. So let's do the same thing now for Orion, because Orion is so important. We'll go back to now the central region of the Orion Nebula, and here we've got the four bright blue stars which were exciting all the filamentary structure. And I would ask you to note these four stars there, and also this bar-like structure running up across the bottom left of the diagram. Now you can see there are great patches of dust here, as well as dust all over the picture. Let's look at the infrared picture, which will see through the dust. It's exactly the same region. Here now is Orion's bar here. There are the four central stars. But look, suddenly we can see a star cluster. It's just like lifting a great veil from in front of the optical picture. In fact, these bright stars are simply the brightest of a whole cluster of stars which is forming in the region of Orion. Now, this picture has been color-coded so that the objects which are only intense far-infrared emitters are shown in the red and yellow color here to the top left, right of the diagram. Now, it turns out these are intensely powerful sources of energy. The amount of luminosity within these regions is about 100,000 times the luminosity of the sun. In other words, there is as much radiant energy coming out in the infrared in these regions as there is coming out in the optical in these very bright blue stars. But we can't see the stars, or protostars, or young stars. They're deeply embedded inside the dust clouds. And what's happening is the same process that the stars are losing energy. The energy is getting absorbed by the dust, which then re-radiates it in the far-infrared waveband. If we now look at the Orion Nebula in the far-infrared, indeed, here it is here, we find it's a terribly intense source indeed. This is the region that we looked at, which was an intense infrared emitter, but now emitting at the far-infrared emission, far-infrared wavebands where the dust is radiating. Now, what does this tell us about star formation? Well, we haven't actually got very far into that story yet. What we've got to do is to take very diffuse gas and concentrate it by a factor of round about 1,000,000 billion times to make something like the sun. Now, fortunately, we know that gravity is very good at pulling things together. If we've got a big enough cloud, then any cloud will collapse simply under gravity if there's no pressure to hold it up. I put on this slide the statement, any fluid or gas is unstable under gravity on a large enough scale. And that's very good news. It means things will collapse. But even better, it collapses in what we call exponentially. That means it can develop very rapidly from a very small perturbation. Now we're going to do an experiment to demonstrate collapse under gravity. We're going to remove the pressure and show how things collapse. And we've got here this experiment to show how a pointer collapses under gravity. It's a rather nice, large, yellow pointer. And Bryson will now perform the experiment. Thank you. I'm sure many of you have done that many times. What we've done now, we have pre-recorded that same sequence earlier with freeze frames about every 0.2 of a second so that we can see what happens. And we're putting up in the top right-hand corner the angle away from the vertical. So it starts at 2 degrees, and now let's run it forward in time. 3 degrees, 4 degrees, 6 degrees, 8 degrees, 11.5 degrees, 16 degrees, 22.5 degrees, 31.5 degrees, 44 degrees, and so on. And the beautiful thing is that in each successive time step, the angle was increasing by the same factor. In fact, it was precisely a factor of 1.4. And this is the whole nature of exponential growth, that in equal time steps, you get the development of the instability by the same factor in equal time intervals. Now, this is such an important point. Let's look at a simple little computer graphics demonstration that we've generated to illustrate exactly this point. Now, I need a computer expert to help me. Would you like to help me? Good, thank you. What's your name?
Zoe.
Zoe, right, Zoe. You're good with computers?
Reasonable.
Reasonable, right. We've got quite a simple thing to do. Now, we've got on the screen here now a representation of a collapsing pole. The pole isn't there yet because we haven't put in the initial angle. But let's try to simulate what we've just done. Let's put in 1 degree. So just put in 1 and then press enter. And now, I don't do anything more. You see that the pole is now just at an angle of 1 degree. And now if you press enter, the pole will collapse. And that is simply the theoretical explanation of a pointer collapsing under gravity. You see it keeps going to bigger and bigger angles as it collapses. But now here's the beautiful thing, because we're going to put in another initial angle. And let's make it extremely tiny, 0.00001 degrees. Okay? So just try putting in 0.000 and a 1, and enter. And now you see the pole is essentially vertical. In fact, you couldn't actually set up a pole that accurately. But now press enter and see what happens. We've got to wait a little bit longer because, remember, it's got to double its angle over a rather long time. But willy-nilly, eventually we get clunk. Exactly the same answer. Thank you very much. That's very well done. Now, you see, the beautiful thing about this exponential growth is that even if we start off with a minuscule deviation away from the vertical, it will always take over and collapse. And that's what happens in interstellar gas clouds. Now, we've got, therefore, to see how it is we can make this process work for interstellar gas clouds. And the question is, do we see these large clouds in which this process can take place? And the answer is yes. If we look within the spiral arm regions of galaxies, we find that the gas is clumped to rather higher densities, and it then cools so that it gets down to temperatures of around about 30 degrees or 100 degrees, and we can observe these huge gas clouds full of molecules by making millimeter wave observations. Now, here is our constellation of Orion. And what I'm now going to do is to overlay on top of this the distribution of cold molecular gas in the Orion constellation. Let's just whip it over. There we are. What that is showing you is where all the carbon monoxide is in the region of the Orion Nebula. And you can see they're gigantic. Huge clouds here, extending way up to the north and way down to the south here. And the beautiful thing is that in the densest region of the clouds, we find the regions where the maximum amount of star formation is occurring. In other words, within these huge clouds, there are peaks where intense star formation activity is taking place. Let's then just look at this model for what's going on. Here's our modern picture then for how we believe the whole process of star formation takes place. There are these giant molecular clouds which are very cold, outlined in orange here, and there are various activities going on in the vicinity of the cloud. Here is a bright young star which is just formed, and this may well be something like the Orion Nebula. It has made young stars and has caused a blister to occur on the surface of the giant molecular cloud. Inside the cloud, there are regions of ionized hydrogen, which we may observe. There are some embedded stars, and then some remarkable outflow sources, which we're going to talk about in just a moment. So that is what the regions in which we have to make stars. What are the problems that we have to overcome? Well, there are three big problems we have to understand in able to make stars, and they are listed on the next picture here. We've got to get rid of three things before we're able to make stars or even protostars. We've got to get rid of energy because the collapse of the gas cloud will heat it up. We've got to get rid of angular momentum or rotation, and we've got to get rid of magnetic fields. Now, we believe we understand the answer to the first one because we've been emphasizing the key role of dust in being able to get rid of energy from the center of these clouds. And in fact, what is happening is that as the cloud collapses, you would expect it to heat up. But that heat is all being taken away and re-radiated by the dust inside the cloud. In fact, in the region of Orion, again, which we've looked at before, this region here is simply showing this enormous luminosity of round about 100,000 times the luminosity of the sun being radiated in the infrared waveband and taking away all what we call the binding energy of the star. So we think we understand that one. Now, the second problem is how to get rid of angular momentum or rotation. Now, this is a rather nasty problem because you see, we're going to start with rather large regions, and they're then going to collapse down into things the size of stars. Now, it's very unlikely that that cloud is just stationary. There's bound to be a tiny little bit of rotation, no matter how small, in that cloud. Now, we're going to show you what happens when that cloud then collapses. Now, we've got here a demonstration of rotation, and I need an assistant to help me with this one. Why don't you come and help me? What's your name? Vicky, right, Vicky. Are you very strong?
Not very.
Are you sure? Okay, we'll try it anyway. Are you seasick often?
No.
Good, right. Well, in that case, I want you to sit on the chair here, right? That's good. Now, Vicky here is a star. She's on television, so she's definitely a star. But we want to think of her as a protostar, someone about to become a star, and therefore she's got a little bit of rotation. Now, of course, there's quite a lot of mass in the outer regions of the gas cloud. And what I'm going to ask Vicky to do is to hold these weights out as far as she can. I'm going to start her rotating, and then she's going to pull them in. Okay, Vicky?
Okay.
Are you happy?
Yeah.
Good. Right. Now, if you put out your arms as far as you can, I'm going to start rotating you rather gently. And when I say go, pull your arms in rapidly. Go. Put them out. Pull them in again. Push them out. Pull them in again. Thank you, Vicky. Splendid. All right? That was terrific. Thank you very much. Now, you saw what happened to Vicky, that as Vicky collapsed, she brought in her arms, then she speeded up. And the same thing is going to happen to stars when they're trying to collapse. So this is one problem we've got to understand. How can we get rid of the rotation of these systems? Now, there's another problem, and that is associated with the magnetic fields. And this is in many ways similar. And we're going to give a demonstration, again, of the problem which arises when magnetic fields are also tied into the collapse. Now, first of all, we're going to show you a very famous demonstration which was first done by Michael Faraday here at the Royal Institution. We've got a star here with a magnetic field in it. There's a dipole magnet underneath here, and Bryson is going to sprinkle some iron filings on this sheet. Now, I hope you've all done this experiment yourself. Beautiful experiment, first done here by Faraday in the Royal Institution. Now, what Bryson does is to tap the sheet, and you'll see the lines of force being defined by the iron filings lining up. Beautiful example. Now, Michael Faraday's great insight was that you can consider magnetic fields to consist of magnetic field lines which have got tension and pressure. The number of magnetic field lines tells you how strong the magnetic field is. Now, when we're dealing with a star which is trying to collapse, we run into a problem. Because even if there are 1 or 2 free electrons in the cloud, a very low density of free electrons, a remarkable phenomenon occurs which is called flux freezing, magnetic flux freezing, in which the magnetic field gets tied on to the cloud. It means that wherever the cloud moves, then likewise the magnetic field is going to be pulled and stretched at the same time. Now, we're going to demonstrate this by a quite magnificent model that's been built by Mr. Mike Sheehy of the Royal Institution to demonstrate exactly this phenomenon. Now, I need someone else to help me with this experiment, someone who's quite strong. Would you like to come and help me? Good, right. Now, you really are strong? A little bit. Good, that's good enough. Now, what we've got here is a model. Come around this side just now, and we'll look at it. We've got here a rotating protostar, and we've got 1 or 2 radial magnetic field lines in this distribution. Now, we're going to rotate this whole thing, but it rotates so that each of these moves at the same velocity, and so the inner ones will get round more rapidly than the outer ones. This is what happens in a collapsing gas cloud. Now, your name is? Jack, right. Now, Jack, what you've got to do is to turn this handle here anti-clockwise when I tell you, rather slowly, and we'll see what happens. Now, let's go 1 rotation anti-clockwise. That's very, and hold on tight. Thank you. Stop there. Now, you see what's happening. The magnetic field is beginning to be wound up by the rotation of the cloud. Let's do 1 more, and hold on tight. Terrific. You see now the magnetic field strength is increasing because the number of field lines per unit area is increasing. Let's have 1 more turn. Ooh, that'll do, that'll do. That's fine. You see, it really is getting, what we're doing is pushing energy into the magnetic field at the expense of the energy in rotation. Now let go. Right? The galaxy unwinds. Thank you very much. Now, you see what a terrible problem this is. That what's going to happen is that the motions in the cloud are going to amplify the magnetic field, and it might go to such an extent that it can actually stop the collapse again. So we've really got a problem. Now, when we look at regions of star formation, what we find is that we don't actually see stuff collapsing, but stuff being ejected. And here is a region where we know there's a star forming here. And these are jets of material being ejected out of the protostar. On the next slide, here's another example of 2 more systems where this is molecular gas going away from us in this direction and towards us in this direction, and similarly in this system. These jets seem to be very common in regions of star formation. The next slide is a Hubble Space Telescope picture of a jet occurring in the center of the Orion Nebula. So these jets seem to be very common in star formation regions. We've summarized what's going on the next slide. here we see a young star here, and it seems to be shooting high-velocity winds out, possibly the poles of this rotating star. We define these by the molecular line observations and by the infrared observations. Now, we're not quite sure how to solve all these problems, but I'm going to show you one rather remarkable way in which we may be able to solve all our problems at one go. It's a model of what might be going on. What we've got here is a protostar, and we've got the magnetic field lines coming out of the pole of the protostar. But of course, the protostar is rotating. So what I'm going to do is to now make our protostar rotate. And as you see, as that starts to rotate, the magnetic field lines get closer and closer together. And so the magnetic field strength is getting stronger and stronger. And in fact, it gets stronger and stronger and stronger. The gas is being pulled in as well, so that we're getting very high densities and very strong magnetic fields occurring in this polar region of the protostar. Now, when this happens, there's a phenomenon known as magnetic flux reconnection, where the magnetic field lines are so close together that they simply reconnect across the top here, and we'll see what happens. What we're going to do is to show this phenomenon of the reconnection of magnetic field lines, but simulating it by this model in which we're using the elastic bands to simulate the properties of the magnetic field lines. So now we're going to put a representative bit of matter in the top here, and we're now going to allow our magnetic field lines to reconnect. Now you see what happened. What happened there was that we did three things at the same time. First of all, the magnetic field suddenly snapped and threw a jet right out of the poles of the rotating protostar. If we'd watched very carefully, we would have seen that the ball was actually rotating at the same time. So it was taking away rotation, it was taking away magnetic fields, and producing jets at the same time. We don't know if this is correct, but it looks a beautiful picture, and something like that almost certainly is involved in the way in which we make stars. Now, there's one final point that you may have noticed about that demonstration, that the rotation prevents the matter falling in along the plane of the protostar, but there's nothing to prevent the matter falling into a plane which is perpendicular to the axis of rotation. And we've actually seen what we think are these disks about protostars in astronomical observations. On the next slide, I'm showing you the James Clerk Maxwell Telescope, which is Britain's large sub-millimeter telescope, which is again in Hawaii. And we've recently observed with it some of these disks about very young stars. The next slide shows that phenomenon. Here is a very young star, and here is the beginnings of a disk about that very young star. Similar observations have been made in the optical waveband. On the next slide, again, here is a dusty disk round about a very bright nearby star. In fact, there are lots of examples nowadays of these dust disks about young stars, and we believe that these are the beginnings of the disks out of which we will make the planets. This is one of the most important areas of astronomy, to understand not only how to make stars, but to make the planets that go along with them. For me, one of the most exciting things is that we can actually now begin to observe the process of evolution of these protoplanetary disks to make planets like our own. That completes our story of star formation. What we've got to take up next time, in the next lecture, is how stars die and how it is that these observations give us crucial clues about how the most powerful sources in the universe, the quasars, work. Thank you.